As mentioned, my name is Drew Mire. I'm CEO of Computrols Incorporated. I was invited last year to speak at NFMT, and I'm glad to be invited back again this year. Last year I spoke by myself, so apparently somebody thought that my presentation was decent, but not good enough to speak by myself again. So they asked me to bring along my colleague, Bryce Jacobs.
How you guys doing? I'm Bryce Jacobs. I'm a software engineer over at Computrols. Today we're going to try to get into machine learning and HVAC controls and kind of how we've been trying to use that and utilize it over at Computrols. And hopefully leave you guys with a general overview or an executive summary of what machine learning is and how it can be leveraged in your building automation systems.
So we're going to break today's presentation up into two pieces. We're going to begin by explaining what machine learning is, where we're seeing machine learning used in our day-to-day lives, and then we're going to get into where that technology that we're seeing in our day-to-day lives is going to be leveraged now and in the future in the building automation industry. Quick background on Computrols. Computrols is a 30-year-old company. It's a leader in the building automation industry. We started 30 years ago as a service provider to third-party building automation systems and evolved into integrating to those third-party integration systems. And that was basically done out of a need. Our ownership saw a need in the market to provide a simple-to-use software platform that can communicate to existing field controllers within a building. As we expanded and grew, we recognized the need to design and manufacture our own product line. So today we have products that encompass HVAC controls, lighting control, access control, and fire alarm. Integration is still a big part of what we do. However, we do have our full product line and those applications as well. All of our products are 100% designed and manufactured at our headquarters in New Orleans.
Okay, so like we talked about or mentioned, we're going to get into machine learning today, and I wanted to kind of start out by defining what machine learning is and kind of what you would find on the internet if you just went and Google searched it. And so what we have here is a definition of machine learning, and I want to read this to you guys, and I want to see if any of you this clears up what you might think of machine learning. So it says, machine learning is an application of artificial intelligence that provides systems the ability to automatically learn and improve from experience without being explicitly programmed. It goes on to say, machine learning focuses on development of computer programs that can access data and use it to learn for themselves. What does that mean? I don't think this clears up anybody's understanding of machine learning. I don't think this does any justice to exactly how it's being used in your day-to-day lives right now. And so let's kind of boil this down. The way that we see this at Computrols is leveraging past performance to predict future assumptions or future performance, or leveraging past history to predict future performance. And so what that means is we're going to gather some data, we're going to model this data, and then we're going to make some assumptions about this data on exactly what we expect it or want to do.
So to kind of elaborate on what Bryce is saying is in summary, machine learning is the practice of leveraging computers, machines, to help us humans process and understand data that we're receiving, and kind of leveraging machines to do the things that machines are good at and leave us humans to do the things that we're good at. And we're going to get into some examples of the things that computers are good at versus the things that us humans are very good at and excel at. Who here thinks that machine learning is a new technology? Actually, it's been around since 1950. In 1950, the Turing test was born. It was a test designed by an engineer named Alan Turing. And basically what the Turing test was is there was a single judge, and then there were four basically hidden contestants in a game-style environment. And one of the four contestants was a machine. And as a result of that, the four contestants was the judge able to identify who the machine was versus the humans. And it proved basically that we could train machines to think as humans, because the judge wasn't able to identify the computer based on the responses to the questions that were being asked. And that's evolved over time. Next big advancement, that was in 1950. Next big advancement was in 1952 when they trained a computer to play checkers. And for a while, I wouldn't say that machine learning technology was necessarily stagnant. It was evolving, but it was evolving very slowly. So you see the next mark line on my timeline here is 2011. And that's kind of when things started changing and drastically excelling. And in 2011 was when IBM's Watson was used to compete against the all-time winning contestants on Jeopardy. And Watson actually won. So that's a huge advancement from somebody learning and a computer learning and understanding to defeat a human in checkers versus somebody, a computer competing against us humans in Jeopardy. Checkers is a very basic game. Jeopardy is a very complicated game. I think we all understand that. So a lot of advancements from that 1952 mark to 2011. However, that was a very large span of time, nearly 60 years. And fast forward to 2013, that same technology, IBM Watson, was beginning to be utilized to help diagnose illnesses in patients, specifically cancer patients. And one of the things that we'll talk about in detail today is machines. One of the things that they're very good at is processing and analyzing large sums of data. Sums of data that it would just be impossible for us humans to analyze and measure and make these predictions. In terms of cancer and the research that's being done, there's a new case every single day across the globe. Having a single doctor trying to process all of these studies that are being done is impossible. However, leveraging the machines for what they're good at helps us to make these similarities and process that data much more efficiently than could be done by humans. Now, Bryce is going to elaborate on this graph that we have on the board here, and what this does is it kind of explains how we've come to excel in machine learning technology.
Sure.
So back to 1952 to that 2011 mark is why did it take so long to get from point A to point B, and then from 2011 to 2013 to have such great advancements? And it's directly related to computing power, and Bryce will explain it a little bit further.
Yeah, sure. So I don't know how many, is anybody familiar with Moore's Law? By show of hands. So yeah, Moore's Law basically is a prediction of how many transistors are going to end up being in our CPUs and how much computing power we're going to end up having. And so what we're kind of seeing is this correlation between how much computing power we have and how much capability we can have in machine learning. And like 10 years ago, or I'm sorry, I read something yesterday, I think it said in 1988, between 1988 and 2014, we're 130,000 times more capable. And between 2014 and now, I think that's doubled over the past couple of years. So just think about that. We were using vacuum tubes back in 1950 and 1952, where we had IBM mainframe computers that took up an entire housing of a warehouse. And so we've come to the point now where these are becoming, your laptop is doing as much more calculations than what that entire warehouse of servers was doing back in the 1950s. So it's become capable now to where we can start making these calculations on the cloud and even in a house where we can process a lot more data a lot more efficiently. So I wanted to kind of distinguish the difference between what a machine is very good at and what a human is very good at. And this is kind of the next segment that we want to get into. So there's a lot of growing that machines still have to do. And on this next slide, we kind of get into, in this next slide, we kind of get into what a human is good at versus what a machine is good at. So over the years and over evolution, humans have become very good at processing images. And this may seem pretty easy for you guys, but a lot of you, I'm sure, are familiar with what this is. This is called a reCAPTCHA. This is hard for a machine to do. It's getting better, and they're breaking these daily. But this is hard for a machine to do because the amount of pixel points that are on these images make it very hard to process this in an efficient rate. So you can see here it says select all images that are oranges. And this is an easy one, but I don't know about you guys. It's getting very hard to start doing these recaptures. I've seen some recently where I've used the accessibility settings to try to get past it because it's in some Sanskrit that I don't understand.
They do some example that I had the other day was identify every car in the pictures, and then they put in trucks and 18-wheelers. Like, well, what do you mean by car? And I'm sitting here questioning what the computer's asking me. It's insane.
It's insert.
Yes, sir.
You guys see the one where I had one yesterday where it's a section of a picture and it says click on all the boxes that are assigned. Well, then there's the stem of the sign.
It's cut off, and what type of sign?
I'm glad I'm not the only one struggling with these.
Yeah, well, I like to consider myself capable, and I mean, they're becoming hard. So this is an easier one that we can kind of take as an example. But if you take this one, for example, it's got the orange up top, and then you can see the ones that have the oranges inside of it. Well, the human brain is very good at processing these images very fast. Over the years, we have a natural neural net that just runs this image past, and we're like, orange. A machine, on the other hand, has to process each pixel and then the relationship of the pixels next to it. And what they've started doing is tracing them, which we'll not get into today. It's outside the scope of this presentation. But each one of these pixels is an RGB matrix, and each one of these pixels have to be correlated to the other one. And for a machine to do that in a fast amount of time, it's not as easy as you may think. And so there's too many data points for this to just be done on the fly. And like I said, it's actually becoming more common for these to be broken through different methods.
So on the flip side of that, there are things that machines are exceptionally good at that us humans lack. One example that I want to use is in terms of memory. I have an app on my phone, one that I'm familiar with using, by the way. I know I had struggled with my phone earlier. And I've had this app for about 3 years. And what this app does is every day at 8 o'clock on the dot every morning, it reminds me of the photos that I've taken in past years. So I can go back for the past 3 years and I'll see in 2016, 2017, 2018, the photos that I took on that day last year. Now, if you asked me where I was on this day last year, I would not be able to tell you. However, the app reminds me and says, hey, this happened this day last year. This is becoming exceptional. I'm a fairly new father, 13-month-old son at home, and so I have photos of him over the course of the past year, and it's starting to bring those photos to me on a day-to-day basis, and I can say, okay, well, I'm looking at my son, and this is him this day last year. So over the course of the next 18 years, as I'm watching him grow up, I'll be reminded year after year. I think that's a very neat feature, and we'll get into how we'll see that same technology leveraged in our BAS systems a little bit later on in the presentation.
Okay, so the second one that we're going to get into is Advantage Machine, right? So I'm sure, as a lot of you know, machines are very good at processing these analytical calculations without ever making a mistake. And so I have two things on the right over here. One is the Bayes theorem. The naive Bayes is one of the building blocks of machine learning for a lot of supervised learning. And then the second one is a polynomial. So I want you guys to kind of walk through this, right? If I had to go solve this polynomial, what would you do?
Well, I'd go to Google.
Yeah, most people would. But if we were in grade school, we would take out a couple sheets of paper and we would block off a couple hours now because we're a little, fuzzy on how to solve a polynomial. We would go through, we would work it out, we would get to the end of it, we would say, okay, we made a mistake, and then we would go back and do it again, right? A machine does this in an amazingly short amount of time without ever making a mistake. And so that's what you have to leverage machines for, is these types of calculations that you don't want to do, or nor would you ever want to do, because that's why we have machines. Calculators came out so we don't have to add stuff over and over again and remember how to do basic math.
So some real world examples that I want to cover with you real quick. Is anybody here familiar with the music app Pandora? Okay. So those of you not familiar, the music app works in such a way that It basically builds the ultimate playlist for your music liking. It tailors a playlist to what your likes and dislikes are. For me, personally, I go into the app, and I'm a big fan of Taylor Swift. So I type in Taylor Swift, and as a result of me saying that I like Taylor Swift, it plays a Taylor Swift song. Since I like it, I hit a thumbs up button. There's a thumbs up, thumbs down button. If I dislike a song, I hit the dislike button. As a result of hitting that like button, similar genre, similar artist is Miley Cyrus. I'm also a huge fan of Miley Cyrus. So I hit the thumbs up button. Again, and it continues to tailor and build a model around my likes and dislikes. So I'm training the machine to get smarter and smarter on the things that I like and dislike. Another example of this is Amazon. I use Amazon on a regular basis. Amazon Prime is one of the great things of our generation. That it's 2-day shipping is ideal. So when I go onto Amazon and it's time for me to buy laundry detergent, I click and I add the laundry detergent to my shopping cart. And as a result of adding the laundry detergent to my shopping cart, it makes a recommendation and says, hey, look, if you're buying laundry detergent, we also recommend that you buy dryer sheets as well. Because if you're in need of laundry detergent, you may also need dryer sheets. That's another example of machine learning technology being used in our day-to-day lives. You also see this in Netflix and where they suggest movies based on movies that you've watched in the past.
So let's critique Drew's bad music choices real quick. And let's get into what exactly the field of machine learning that is most relevant to building automation systems. So supervised machine learning is one of the fields of machine learning, and it hinges on the ability to gather data, model data, and make assumptions on that data. So in the case of the Pandora example, and when Drew said that he likes to listen to Taylor Swift, when Drew is listening to Taylor Swift for 3 hours, it's gathering all this data and it's trying to make a model around Drew himself. Drew is the model. When Drew goes and does something like hit an up button or the like button or the dislike button, he's training that algorithm, like he said, to be more tailored to Drew himself, right? And so basically he listens to Taylor Swift and the algorithm says, what other genres might he like, right? Okay, he likes Taylor Swift. Is he going to like Katy Perry? Okay, let's suggest that as a station. When they make that suggestion, it then needs to validate that that was a good suggestion or it was a bad suggestion, and that's where the supervised machine learning comes in. The validation is how we tweak the model to be more specific to Drew. So every time that Drew does something like listen to a station or give us the up or down button, the like or dislike, we're refining that model so every time that he goes in there, he's getting more specific music choices. And that's how Amazon and these other companies have come to be. They have to make suggestions that are going to make them money. And at the end of the day, these impressions are very costly and they have to get it right.
So let's get into the building automation section of this presentation. We'll kind of change courses here and discuss, okay, well, how are we going to take the technologies that you're describing and how are they going to be related into my building automation system? So first I want to begin by discussing the building automation system of today versus the building automation system of tomorrow. Historically, a building automation system has consisted of 3 primary layers, and that is a head-end PC, network infrastructure, and field controllers. The head-end PC is connected to the field controllers via the network infrastructure that I mentioned, and the head-end PC runs a software that's used to display all the data that's being collected from the field and also control the points that are out in the field. The building automation system of tomorrow, and some of you may have already seen this happen, is we're taking that head-end PC and removing it from your building. And it's going to a web-based system or a cloud-based system you may have heard it referred to as. And what that's doing is it's taking that head-end PC, putting it in a data center, and you're able to remotely access that PC or that software user interface via your mobile device, your tablet, your laptop, so on and so forth. Anything that has a web browser, basically. We're also looking into the future and seeing where these field controllers that we have had historically are turning into gateways or hubs to process wireless devices and control and manipulate things through these gateways rather than field controllers, and leveraging wireless networks versus hardwired networks.
And one important thing to note from that is that the ability to send this up to the cloud and use the computing resources of these widely available Amazon Cloud, Google Cloud, or your own server farm has really enabled us to be able to do these types of calculations in a fashion that'll be quick enough to where we can use them to make assumptions about a building. And so now that we've kind of given you a definition, a brief overview of what exactly machine learning is, let's get into the HVAC side of it, and let's talk about exactly how this works in an HVAC system, right? Well, the first thing is we need to gather the history. Like in the Pandora example, Drew listened to the station and he was able to provide Pandora with enough history that it could start making assumptions on what exactly he might like, right? Well, how do we do that in a building automation system? Well, most building automation systems, if not all, have the capability of storing this history on all these points that exist, right? So go ahead, store the points, and then we have to do something with those points. In the algorithm, we have to tag these points up and we have to make it to where it's flattened out enough to where we can run assumptions on it and make these models come to fruition.
And this is one of the areas where the building automation industry is really primed for leveraging machine learning technology, because like many of you here are aware, many BASs have points that have prefixes on them. So typically a normal BAS, you'll have AHU1 start-stop, AHU1 status, AHU1 cold deck temperature, AHU1 supply air temperature, so on and so forth. You already have a tag there. So you're able to, this makes our job a little bit easier in terms of we have those prefixes defining a piece of equipment as an air handler unit, and then we can feed that data to software guys like Bryce, and he can really do something with it.
Yeah, and the tagging part of it, we'll get into the challenges of that later. But after we tag it, after we get it to a point where we could actually use it, right, then we have to build a model, okay? Like we talked about in Pandora, it's building a model around Drew. So how do we do that in an HVAC system? Well, the HVAC system and the building automation systems historically have been kind of loosely modeled through just having these points and these tags and having this structured but not really structured way of introducing points into a system. And so building a model can be something as simple as, for a simple example, I want to know when the HVAC system is going to make my temperature at 65 degrees in zone 1 or something of that sort. And so that would be our model. When can I expect this zone to be 65 degrees? That's the prediction, and then we have to validate that model. So like we validated with the thumbs up or the thumbs down in the Pandora example, we now have to validate, did I make a good assumption on the data? That involves how close was I on my estimation that in 3.5 hours I was going to be at 68 degrees. Was I 10% off? Was I 5% off? Was I nowhere close? And then refine that model to be more accurate the next time that we do it, so we slowly move towards being very, very accurate over time.
Okay, so how are we going to use this in HVAC control applications? Where is this technology? You guys keep talking about Pandora and Amazon and Netflix. How is this relevant to the building automation industry? And I'm going to provide 3 basic examples here on how you may see this technology leveraged in the future. I'm sure many of you here are familiar with optimal start-stop. Anybody not familiar, optimal start-stop basically runs a very simple algorithm within your BAS, and essentially what it's doing is finding the very last minute that a piece of equipment can start to achieve a set point at a given point in time, which is typically the occupancy time for a space in a building. With machine learning technology and the amount of data that we're able to process and get within our building automation systems today, we're going to see optimal start-stop go away. And the reason we're going to see optimal start-stop go away is because there's going to be newer, better ways to run these models, to achieve comfort while saving energy at the same time. And what we're going to do, one of the things that Bryce mentioned is historical data is huge. One of the features of Computrols building automation software is the fact that we store histories on all points all the time from system inception. So we have this data from years and years and years, and we're feeding that to our machine learning technology that Bryce and his team is working on developing. And what that's doing is taking past historical degree days, analyzing that data, seeing how a building operated this day last year when it was a degree day of this nature. We're also taking weather forecast data. So we can get that weather forecast data into the BAS and say, okay, this is what we're predicting the temperature to be tomorrow. This is what we're anticipating the load for the building to be. This is how we ran on like degree days the last 5 years. And this is what we recommend as a result of this. So these are things that large sums of data that machines can process and make predictions and run these analysis in the background and help us to run the buildings more efficiently while maintaining that comfort level. So that's one example of where you'll see a shift from something that we've used for the last 20 years to operate our buildings in terms of optimal start-stop. This is where we're going in the future, is being able to take lots and lots of data, as I mentioned, historical and predictive, and then make assumptions, validate these models that Bryce was mentioning as a part of that model. Another example is going to be in regards to preventive maintenance, and this is something that we had a bit of a pre-discussion with one of the attendees before we started the presentation. And one example is going to be the belt on a fan motor. We had mentioned that as an example, machines are very good at processing large sums of data. So you take a high-rise building, there may be 50 air handling units in a high-rise building, you have 50 fan belts that you have to be concerned with. Maybe over the course of a 6-month period to a year-long period, the amps begin incrementally increasing on the CT that's connected to that motor. These are very small incremental changes that you and I as humans would likely not see. And it's understandable because you have 50 fan belts and you're not seeing these incremental increases. However, the machine can process and say, hey, look, over the course of the last 6 months, a year, we've had incremental increases in the amperage on this fan motor. As a result, we're recommending that you go do a preventive maintenance call before the belt pops or slips. And the last example is going to be what we refer to as BAS and fast forward. And this is similar, yet a little bit more advanced than what I talked about in terms of optimal start-stop. Is we're going to be able to, in the future, take that large sum of data that we have, predictive weather data, historical data, and use this and play out our BAS and what we're calling fast-forward motion. It's similar to DVR on your TV. This is what we're predicting. This is how your day is going to play out tomorrow. And we can even make assumptions and run an analytics and say, well, as a result of what we're predicting, at 4 p.m. you can cut down on chill, you can turn off chiller 4 because you're not going to lose any level of comfort and you're going to reach your peak demand at 3:45, and we recommend that you shut it off just before then, and you'll maintain the comfort level in the building and also increase your efficiency. So in essence, basically, what we're getting at is the computers can run a lot of analysis, take a lot of data, and process that data very quickly, and then play it out for you and say, hey, this is what you can expect to see. It's going to basically give you all your values and play it out in real time so that you understand in advance how your building is going to operate, and it'll spell it out for you. It'll lay all those values out.
So as we go through this machine learning and as we've learned kind of how this was going to play out in our system, we've come across a couple challenges that I wanted to kind of address and kind of the stuff that's still ongoing with us and our team. The first one is, as you can imagine, a building automation system, when we talk about processing data in the cloud, right? If I have a building with 60,000 data points and they're banging at once a second, or even half of that, it's a lot of bandwidth, it's a lot of storage, it's network in infrastructure that can fail. And so just storing this data can become costly, and it also it requires a little bit of it's been a design challenge just to make sure that we're not doing too much to the building as far as their bandwidth and just hammering it out. So you end up doing things like compressing all this data and trying to make it clean to the point where we're not going to be putting too much of a burden on the building itself. The second thing was, and we talked about it earlier, tagging data is something that's a little time consuming at the startup of the project. In CBAS, we're fortunate enough to have the structure of the points themselves. And what that provides us with is the ability to do some inference that you're not capable of doing in most cases. And so you have a lot of these different standards coming together, such as Project Haystack, and I think BACnet has a web services standard, if I'm not mistaken. And they're trying to standardize it to a point where it's not as much of a burden when you go to set these systems up. Cleaning data is a bottleneck for any machine learning solution. So you end up doing things like linear regression to try to clean this data and linearize it, because I want you to imagine an HVAC system or any system in a building automation system, any equipment in a building automation system, how much noise is introduced by the environment. If I go drop something in a room, these sensors are becoming more and more sensitive. That shows up on a graph like a seismograph at some times. And so just cleaning and filtering this data to a point where it's usable, they have PhD theses on it right now. And lastly, validating the model, it's not as straightforward as you might think it is. So validating the model in our case, like I talked about earlier, how far off was I? Was I 5%, 10%? Well, it's not always that simple. Did I even get to set point? There's a lot of edge cases that end up happening in the building automation system that you have to be prepared to catch, or else you're not going to have an efficient solution that actually provides value.
I also wanted to get into, I failed to mention on the previous slide, but I had given an example earlier in the presentation about the phone app that I utilize, and it reminds me of photos from historical days over the course of the past 3 years in my instance. And this is very similar to what you're going to see in the BAS of the future, in terms of it's going to remind you of how your building operated on like degree days in the past. It's going to say, hey, this is what you can expect as a result of historical data and what we're predicting for the future. And then to go back on to the first slide that I did on the BAS system of today versus the BAS system of tomorrow. And based on what we're discussing today, the BAS system of tomorrow, building automation system of tomorrow, is here today. It's coming, and you should see massive amounts of technology upgrades in the next couple of years. And the technology is here today. We already talked about the cloud and web-based systems being here. And what that really does for you as a result of being cloud or web-based systems is you're not relying on a single piece of hardware, a machine in your building, physically located in your building. You're now clustering large servers and data centers, and they're running analysis and taking a look at like buildings and making comparative models and really getting smarter and smarter and smarter. And this is a direct result of cloud computing, and this is something that we touched base with on the Moore's law, was it?
Yes.
And so the computing power is really enabling us to advance this technology very quickly. So again, the BAS system of tomorrow is here today. These are the things that you should be asking your vendors about and reaching out to them and saying, hey, look, I attended a presentation, talked about machine learning. What is on the horizon? What can I expect to see get out of my building automation system in the next couple of years? Any questions?